Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 2 on geometric sequences. Now this is directly going to build off of our last lesson, Lesson 1, on exponentially increasing and decreasing sequences. So you really want to make sure that you've seen that and that you've got kind of a nice review of exponents and things like that before getting into this particular lesson. But that being said, let's launch right into it. You're going to want to make sure that you've got a calculator handy because we're going to be doing a lot of work with exponents today and a lot of large numbers and some very small numbers. So make sure to have those handy. All right, so here we go, sequences. Now recall from a few units ago that a sequence is just a list of numbers in a particular order. So far, what we've done is we've studied arithmetic sequences whose consecutive terms have a constant difference. In other words, you have to add the same amount or subtract the same amount to get from one term or element of the sequence to the next term. So let's just review an arithmetic sequence in the first problem. Here we go. Exercise number 1. The first four terms of an arithmetic sequence are shown below. 9, 14, 19, 24. Letter A, what is the common difference for this sequence? Illustrate. All right, so pause the video now and see if you can figure out what the common difference of this sequence is. All right, well, we always want to figure out the common difference, no matter whether it's increasing or decreasing, by taking the second term and subtracting the first term. In this case, that's 5. Now, I'm going to do this for all of them, though. The third term minus the second term is 5, and the fourth term minus the third term is 5. Right? And what this is telling us is something that's probably pretty obvious by just looking at the sequence. I get to the next element each time by adding 5. Each time I'm going to add 5 again and again and again. Now let's take a look at letter B. Find the value of A of 20, so the 20th term, without listing all 20 terms. All right, see if you can remember how to do this, and as a key, right, the real question is, how many times do you have to add 5 to the number 9 in order to get to the 20th term? Pause the video now and see if you can remember how to do this. Well, what I always encourage people to do is think about it this way. I have to add 5 to 9 once to get to the second term. I have to add 5 to 9 twice to get to the third term, 3 times to get to the fourth term, 4 times to get to the fifth term, etc. So I will have to add 5 to the number 9 19 times to get to the 20th term. So A sub 20 is going to be 9 plus 19 of those 5s, right? One less than the number of terms, all right? So now I'm going to just kind of exit this real quick. Let's pull that up, do a little calculation here. All right, I've got 9 plus 19 times 5. Simple enough. That's equal to 104, all right? Now the real key there is two things, right? Reviewing what an arithmetic sequence is, i.e. you add or subtract the same number each time to get to the next term, and really key, to get to a certain term, you always add that difference one less time than the number of terms you're looking at, okay? So I had to add 5 19 times to get to that 20th term. All right. Let's head to the next slide. Here we go. Let's now talk about what are known as geometric sequences. When the terms of a sequence increase or decrease exponentially, which is what we saw in the last lesson, there's a common ratio or factor. We call it a geometric sequence. So in the last lesson, we actually looked at a number of geometric sequences. We did. We called them exponentially increasing and decreasing sequences, but they were actually all these geometric sequences. The common ratio is typically represented by the letter R for ratio. Kind of makes sense. So let's take a look at exercise number 2 with some geometric sequences. For each of the following geometric sequences, identify the common ratio R and then fill in the next two terms. All right, now again, this R value is what we're going to multiply each term by to get the next term, and the next term, and the next term, and the next term. And I really want you to understand, right? The way I can think about this, let's talk about letter A, is I could think about it as, well, I have to do 2 times r to get 6. So what is r equal to? R is equal to 6 divided by 2, right? Or 3. Now I could also do r is equal to 18 divided by 6, which is also 3, right? Common ratio, right? Same number. All right, and we can always do that. We can always figure out the common ratio from taking the second term and dividing it by the first term, or taking the third term and dividing it by the second term, etc. Now, how do we then get the fourth and the fifth terms? Well, that's simple enough, right? Let me just get rid of this. So for instance, in this case, A4 is going to be 18 times 3, right? And that's going to be 54. On the other hand, A5 is going to be 54 times 3, which is 150 plus 12, which is 162, right? So it's easy enough, right? Once you know you have a geometric sequence and you know that each term of a geometric sequence is just this number, r, times the previous term, it's pretty easy. Now in the last lesson, all the ratios that we looked at were positive numbers. But for a geometric sequence, it doesn't actually have to be a positive number. It could also be a negative number. Why don't you go ahead and tackle letter B, and then we'll talk about that one together. All right, so letter B is a great example of a geometric sequence where the common ratio is actually a negative number, right? And again, you can think of it this way, right? R is equal to negative 20 divided by 4, which is negative 5. And you can check that as well. R would be 100 divided by negative 20, which is also equal to negative 5. So the ratio here in this case is negative 5, all right? And now it's pretty easy, right? To get the next term, I'm going to take 100 and multiply it by negative 5, and that would be negative 500. To get to the term after that, I would take negative 500, multiply it by negative 5, right? A negative times a negative is a positive, and that would end up being 2,500. And of course, you could use your calculator to do that. I was doing it in my head because they were relatively easy numbers to work with. Now, in this case, right, we had a number that was a whole number. In this case, we had a negative whole number, if you will, right? Here's going to be a situation where that sequence is decreasing, and so now our ratio won't be a whole number anymore. Why don't you pause the video now and see if you can figure out what's going on in letter C. All right, you have to be very careful here because it's easy to see 16, 8, and 4 and say, I've got a common ratio of 2. But if you had a common ratio of 2, then the next number would be 8, and the number after that would be 16, and that's not the way these work. These sequences, especially when r is positive, are either all going to be decreasing or all going to be increasing. When the r is negative, then it's weird because you're going to flip-flop between negatives and positives, so that's not quite the same. But in this case, again, just trust the math, right? R is going to be 8 divided by 16, and that's 1/2. And again, we can test it, right? The next one would be 4 divided by 8, and that's also 1/2. So in this situation, r is 1/2 or 0.5, whichever you prefer. Now, right, we can take 4, multiply it by 1/2, and of course we get 2. Then we can take 2 and multiply it by 1/2, and we get 1. All right? All of these, all three situations, geometric sequences. To get from one term to the next term, you multiply by the same number each time. Easy enough, right? Very similar to an arithmetic sequence where you add or subtract by the same amount each time. Now, as with arithmetic sequences, we should be able to predict any given term of a geometric sequence if we know its first term and how many times we've multiplied by r, all right? So let's take a look at that in exercise number 3. A geometric sequence has a first term of 5 and a common ratio of 3. Letter A, find the values of A2, A3, and A4. Write each as an extended product to see a pattern, but also find the final result. All right, let's talk about this, right? So the idea here is that A2 would be 5 times 3. All right, 5 times 3. Or better yet, 5 times 3 to the first. That's easy enough. That's 15. All right, so no big deal there. Okay, nothing interesting about A2. On the other hand, A3 would be 15 times 3. And I know 15 times 3 is 45. I get that. But keep in mind that that's 5 times 3 times 3, or 5 times 3 to the second, which would be 45. All right? And what I really want to be keying in on is these expressions, right? And finally, A4 is going to be A3 times 3, which is 5 times 3 times 3 times 3, right? Which is 5 times 3 to the third. And that's going to be 135. The ultimate answer here I'm not too concerned with. I'm looking for a pattern. So take a look at that, right? A2 is A1 times 3 to the first. A3 is A1 times 3 to the second. A4 is A1 times 3 to the third. So let's take a look at letter B. Determine the values of A sub 10 and A sub 20. Show the calculations you use. All right, so now I'm hoping that you see the general pattern and you can just figure out what's going on here. So pause the video now. Both of these answers are going to be relatively large, of course, with A20 being much larger. All right, see what you get as your answers. All right, well, the key is, and we talked about this in the last lesson, we're always going to be multiplying one less time than the term that we're looking for. That should sound familiar with arithmetic sequences, right? We added one last time, or one less time. Here we're multiplying by one less time. So, in other words, A10 will be equal to that 5, and we'll multiply by 3, but only 9 times. Again, slightly bigger number than what I want to deal with right now. 5 times 3 to the 9th is going to be 98,415. 98,415. Great, and that's just A10. Now you got to watch out, because the last thing you'd ever want to do is say, well, A20 should just be twice A10 because, well, 20 is twice 10. By the way, no, that doesn't work, right? A4 wasn't twice A2, 135 versus 15. But, of course, A20 is now going to be 5 times 3 to the 19th, and I might as well get ready for how big this thing's going to be. All right, 5 times 3 to the 19th. Oh my, oh geez. I don't even know if I want to write this down. Let's see, 5811307. I do kind of want to write it down though. 335, so that is, whoo, haha. That is 5,811,307,335. That's awesome. And it also illustrates exponential growth, right? So in other words, by the 20th term, this beast is huge. All right, let's take a look at exercise 4. This is very important. Okay, so let's go for it. Given a geometric sequence that has a first term being given by A1 and a common ratio given by R, do the following. Letter A, create a formula for the nth term of this sequence, i.e. A sub n. All right, we did this a few units ago with arithmetic sequences. See if you can come up with the formula that predicts the nth term, A sub n, right? So we're going to start by writing this down. The nth term of any geometric sequence based on its first term, A1, based on its common ratio, R, and based on the variable n. Pause the video now and see if you can figure out what it is. All right, well, it's actually kind of similar to the arithmetic sequence formula. right? So we're going to take always my first term, and I'm going to multiply it by the common ratio raised to 1 less power than the number of terms. And that's exactly, of course, what I did in exercise 3, letter B. To find the 10th term, I took the first term and I multiplied it by the common ratio 9 times. To get to the 20th term, I took the first term and multiplied it by the common ratio 19 times, 1 less time. Now let's take a look at letter B. Use your formula to predict the 6th term of a geometric sequence whose first term is 972 and whose common ratio is 2/3. All right, well, go for it. See what you get. All right, well, here we go. Even if you don't memorize the formula, as long as you understand what's been going on, right? The 6th term is going to be that first term, 972, times that common ratio 2/3, and then I'm going to multiply it by that 2/3 1 less time. Okay? So real quick, let me just clear this out. What do I have? 972 times 2/3. Make sure that 2/3 is in parentheses, raised to the 5th, and we get 128. All right, that's it. Simple as that. Geometric sequences are very, very similar to arithmetic sequences, except instead of adding the same amount each time, you multiply this by the same amount, and we should be able to figure out what any given term is as long as we've got that first term and that common ratio. Now, it's kind of interesting to compare how quickly the terms increase in an arithmetic sequence compared to a geometric sequence. Of course, this is assuming that they're both getting larger, i.e. for the arithmetic sequence, you're adding a positive number, and for a geometric sequence, you're multiplying by a number greater than 1. All right, and let's look at a classic example. Every student who ever looks at arithmetic sequences and geometric sequences does this example because it's a wonderful, wonderful illustration. Let's take a look at exercise number 5. You have just won a very strange lottery. The lottery promises to give you money each day for a 30-day month based on one of the following 2 options. Option 1, you can receive $1,000 on the first day, $2,000 on the second day, $3,000 on the third day, etc. in this arithmetic sequence. Or option 2, you can receive $0.01 or 1 penny on the first day, $0.02 or 2 pennies on the second day, etc., $0.04 on the third day, $0.08 on the fourth, etc. in this geometric sequence. Of the 2 options, which would result in the larger payoff on the 30th day only? Show work that supports your answer. In other words, I'm not going to worry about what the sum total is, although that's an interesting question all by itself. That's beyond the scope of this course. What I'm interested in just, if you showed up on the 30th day, how much would you get under option 1 and how much would you get under option 2? Well, I'd like you to pause the video now and play around with both of these scenarios and see if you can figure out how much you would get on the 30th day in both situations. All right, well, it's a little bit silly to do almost any kind of calculations for option 1, but I'm gonna kind of pretend that this is just your garden variety arithmetic sequence, right? By the way, right, I would hope that many of you sort of at first glance would be like, oh yeah, option 1, man, $1,000 on the first day compared to like a penny? $2,000 on the second day compared to 2 pennies? I mean, it really looks like option 1 is your go-to option, right? But, I mean, option 1, let's take a look at that. Again, it's a little bit silly. We're going to get a result here that's completely predictable. If I write using sequence notation, right, I would have what I got on the first day plus, right, 29, because we're talking about 30, times how much each one differs. So that's times 1,000. All right, and not surprisingly, that means you're going to get $30,000 on the 30th day. I like that. That's a good payoff, right? $30,000 on the 30th day. Again, it's a little bit of a silly situation because, I mean, if you're getting 1,000 on the first day, 2,000 on the second day, 3,000 on the third day, you're obviously getting 30,000 on the 30th day. But it is still an arithmetic sequence, right? You're starting with 1,000. The common difference is 1,000, and you add it on 29 times to get to that 30th day. Now let's look at the more complicated math, right? Option 2. Now in option 2, right, your original amount, let me extend this a little bit. Your original amount is 0. Actually, let me use a different character. We'll go with B. B30 in this case, right, will be my original amount, which is 0.01, times the common ratio. Well, we're doubling each day, raised to the 29th. So before we plug that into the calculator, let's just make sure we understand it, right? For a geometric sequence, we always take the first term, which is 0.01 in this case, multiply it by the common ratio, which is 2, right? Hopefully everyone recognizes, right? We're going 0.02, 0.01, 0.02, 0.04, 0.08, so we're doubling each time. And again, we're going to raise it to the 29th because we do it one less time than the number of terms. All right, let's take a look at this. I mean, surely this will be much smaller than 30,000. 0.01 times 2 raised to the 29th. Oh my goodness. All right, 5.36871 E6. That's scientific notation. E6 means it's times 10 to the 6th. That is a huge number. All right, so B30. Where is it? Come back. And that's actually 5,368,000 710. Wow, that is a lot. All right, think about this for a second, right? We are doubling and doubling and doubling and doubling, and it grows so much faster than this one that even though this one starts off with such larger amounts, by the 30th day, right, this one's paying you 30,000, this one's paying you 5 million. 5 million and some change, right? So much that I'm just kind of like ignoring the 368,710, which shouldn't be ignored. That's a lot of money too. All right, let's take a look at one last one. Okay, now we can graph sequences. All right, we graphed an arithmetic sequence at one point, and graphs of the terms of a geometric sequence can really give us a sense for how they behave, right? We can then see them, if you will. So let's take a look at one simple example of a graph of a geometric sequence. Exercise number 5. Consider a geometric sequence whose first term is 8 and whose common ratio is 1/2. Letter A asks us to write out and plot the first 5 terms of the sequence. All right. That should be pretty simple. Why don't you pause the video now and write out what A1 is, what A2 is. Oh, here, let me get you started. A1 is equal to 8, right? So now you figure out what A2, A3, A4, A5 is, right? The x-axis here is just the number of terms. So in other words, I can even plot the first term, right? That's 1, 8, right? I want you to figure out all the rest and plot them. Pause the video now. All right, well, A2, right? A2 is going to be 8 times 1/2, or 4. Let me plot that. A3 is going to be 4 times 1/2, which is 2. A4 is going to be 2 times 1/2, which is 1. And A5 is going to be 1 times 1/2, which is just 1/2. Now I'm not going to connect these with a smooth curve again. We talked about that once before, right? Because there are no points in between here. These are terms of a sequence, all right? But letter B is important. Is this a linear pattern? Well, is it a linear pattern? What does that even mean? Pause the video now and see what you think. And the answer is no, right? And you could justify it in a lot of ways, but one way you could justify it is simply these points don't fall on a straight line, right? They don't fall on a straight line. If I started a line here and I connected it down here, right? If I connected these two, with a straight line, the other points don't fall on it. Another way to say it is that they don't have a common difference, right? So in other words, if it was a linear pattern, then there'd be a constant rate of change, right? As I went over 1, I went down 4. But then I went over 1 and I went down 2. Then I went over 1 and I went down 1. Then I went over 1 and went down a half. Right? With a linear pattern, every increase in x will give you the same increase or decrease in y. But here, that's not happening, right? So they don't fall on a line and don't have a constant rate of change. Right? And that's important because if they did, then we would just be back to linear functions and arithmetic sequences, right? Exponentials have curves to them, right? There's a curve here. It's changing. The rate that it's actually going at is changing as the sequence gets larger. All right, so this whole unit is going to be all about exponential growth and decrease. And one place that we see that are in these geometric sequences. Sequences where each term differs from the last term by a constant factor or constant ratio, right? Now, if the sequence is increasing, that ratio is greater than 1. If the sequence is decreasing, then that ratio is between 0 and 1. This is assuming that the ratio is positive. The ratio can be sometimes negative, but that's kind of rare, and you just have to play around with a little bit of that on the homework. All right. Now, we'll be seeing and calling back to geometric sequences throughout this unit, so you will get more work with them. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.